Our claim is that iron is the most stable element. First off, the high mass defect of iron, which is 0.59938, is a major contributor to iron being a highly stable element. The mass effect is the difference between the mass of the nucleus and the mass of the nucleons combined. So Md minus the sum of Mp plus Mn is subtracted by Mo is the formula used to represent the mass effect. So in this equation, Md represents the mass effect, Mp represents the total mass of the protons, Mn is the total mass of the neutrons, and Mo represents the atomic mass of the element. So you can see from our slide, the number of protons is 26, which is multiplied by the mass of each proton, which is 1.00728. Likewise, there are 30 neutrons in one atom of iron, and that is multiplied by which is the mass of one neutron, 1.00867. So in our equation, the mass defect turned out to be 0.59938. This means that the difference, which is the mass defect, is the energy that keeps the nucleus bound together. Because of iron's high mass defect, its nucleus is able to be tightly bound, which makes the nucleus harder to separate into its nucleons. Additionally, the mass energy equivalence formula can be used to convert the mass effect into nuclear binding energy. The mass energy equivalence formula is the famous equation E equals mc squared. E is the energy, m is the mass effect, and c is the speed of light. Again, the higher binding energy correlates to iron being the most stable element. So our graph shows that iron, which is circled in red, is near the top of the y-axis. The y-axis represents the binding energy, and as we've explained previously, the binding energy also shows that mass effect is very high.